Hello everyone and welcome back to a brand new video. And in this video, I will be solving problem E, that is critical hit, from Atcoder beginner contest 280. So let's move on to the solution. But before we move on to the solution, I want to tell you guys about Newton School's coding contest. So Newton School organizes coding contest every month. You guys can solve some quality problems and also compete against top coders in the world. This will be a good opportunity to benchmark yourself where you guys are lying in respect to other students in India or around the world. Not only that, along with this, you can also win some cash prizes. You can win rewards up to rupees 90,000. You can also win scholarships up to rupees 20,000. And along with this, there will also be some job opportunities. So this month, the contest will be on 30th of November. It will be around 2.5 hours from 9 p.m. to 11:30 p.m. So do not forget to sign up. The link will be in the description. So do go and sign up from there. So in the problem, we have been given an integer n, where n can be up to 10 to the power 5. And here n represents the health of a monster, right? And we want to kill the monster. So to kill the monster, we can strike it. And a strike will either hit a damage of 2 or it will either hit a damage of 1, right? So to decide this, we have been given some probability. So we have been given an integer p, where p lies from 0 up to 100, and there is a p over 100 chance that our strike will have a damage of 2, and there is a 100 minus p over 100 chance that our strike will have a damage of 1. Given this, we have to find the expected number of strikes, or you can say hits, that are required to kill the monster. Or more formally, you can say that expected number of hits such that health of the monsters becomes less than equal to 0. So that is the problem. Given a monster of health n and some probability p, find the expected number of hits that are required to make the health of monster less than equal to 0, right? So let's see how we can solve this. So I would like to rephrase the problem, right? Because if you are able to visualize the problem, I think it is much easier to solve. So let's say I rephrase the problem and I will convert this into a jumping game, right? So let's say you just have a horizontal strip starting from 0, 1, 2, 3, so on up to n and n plus 1, right? So I can say that initially we are at 0 and I can convert the strikes into jumps, right? So I can make a jump of size 2 with probability p by 100, and I can make a jump of size 1 with probability 100 minus p over 100, right? And saying that my health is less than equal to 0 is similar to saying that I reach cell n or n plus 1, right? So we can convert the entire problem into a horizontal strip of size n plus 2, and then my answer is just the number of jumps that are required to reach cell n or n plus 1 starting from cell 0, right? So I can say that my answer is just expected number of jumps needed to reach cell n or n plus 1 starting from 0, right? These two problems are similar, or you can say equivalent. But this problem seems quite hard to understand or solve when we have been given this probability p, right? So let's, for the time being, try to fix this probability p and try to solve an easier problem, right? So first we will fix or ignore this probability p, try to solve an easier problem, and then extend that solution to the whole problem, right? So let's say for the time being, your probability p is equal to 100, right? So that means you will always make a jump of size 2, right? So if I try to draw this out, I will get something like this. I have 0, 1, 2, 3, so on up to n plus 1. So I will start from 0, I will go to 2, I will go to 4, and so on. At some point I will either reach n or I will either reach n plus 1, right? So what is your answer here? What is your answer here? I can say that my answer here is the number of cells that I visit from 1 to n minus 1 plus 1, right? Because this one extra move is required to go to cell n or n plus 1. But all these moves are the number of cells that I visit from 1 to n minus 1, right? So I can say that my answer is equal to number of cells I visit from 1 to n minus 1, right? And then plus one extra move. This is to reach n or n plus 1, right? This is to reach n or n plus 1, right? So this will be the answer when you are able to make a single jump, right, of a fixed size. So I can extend this even further, right? So let's say you have a chess piece, right? Let's say the size of this chess piece is 1, right? Initially this is at block 0. I am 1, 2, 3, 4, so on up to n and n plus 1, right? Initially this chess piece is at cell 0. Then I make a jump of size 2. This comes to block 2, right here. Then it goes to 4, and then it will keep jumping, and it will reach cell either n or n plus 1, right? It will reach either of the cells. So you can see that the total number of pieces on block 1 is equal to 0. On block 2 we have a piece of size 1, so I can put a 1 here. On block 3, or you can say on cell 3, I have 0 pieces. On cell 4 I have 1 piece. So I can find the number of pieces that were on a cell, right? And you can say that your answer is just number of pieces on all cells from 1 to n minus 1, right? Because you are making these moves, right? You are making these moves. So we can count the number of pieces that were on every cell from 1 to n minus 1, right? And then one extra move, then 1 plus 1 to reach cell n or n plus 1, right? So we can say number of pieces on all cells from 1 to n minus 1 plus one extra move to reach n or n plus 1, right? So I hope you are able to see the solution now, kind of. So initially we defined that we can make jumps of size 2. So you can visualize a chess piece here, right? And I told you that your answer is number of cells that we visit from 1 to n minus 1, and then one extra move to reach n plus 1, right? And to understand it even better, we can see as a chess piece that is moving to the cells. So chess piece will be on cell 0 first, then it will move to 2, then to 4, then so on up to until it reaches n or n plus 1, right? So we just need to count the contribution that a chess piece gives from cells from 1 to n minus 1, right? On cell 1, it will give a contribution of 0. On cell 2, it will give a contribution of 1, and so on. You just count the number of contribution that the piece gives from all cells from 1 to n minus 1, and then you add just one extra move to reach cell n or n plus 1. But this was the case when your piece was moving with p equal to 100, right? You were always making a jump of size 2. But what will happen to the piece when your p is not 100, right? So let's say your p is equal to 60, right, for a change. So let's say this is n plus 1, this is 0, 1, 2, 3, so on up to, right? So initially you have a piece of size 1 here, right? But in this case, your p is equal to 60, right? So that means your 0.6 part will move to 2, and your 0.4 part will move to 1. Similarly, now you are on the following step, right? So this 0.6 part then will move to 4, and then 0.4 part of this will move to 3, right? So you can say that 0.6 into 0.6 will move to this cell, and 0.6 into 0.4 will move to this cell. Similarly, you can do the same thing for the piece on cell 1, right? So you can see that previously your entire piece was moving. That's why we were easily able to see number of cells that we visit from 1 to n minus 1, right? But in this case, now your piece is breaking up, right? So in this case, your answer is just like sum the contribution of pieces, sum the contribution of piece from 1 to n minus 1, and then add one extra move to reach cell n or n plus 1, right? So I will just go over all the cells from 1 to n minus 1, and I will count the contribution that this piece gives to all these cells, and then I will add one extra move that is required to reach n and n plus 1, right? So this makes the problem very much easier, right? So now we just need to write a dp and some transitions, and then we can find the sum for all the dp states from 1 to n minus 1, and then add just one extra move for reaching n or n plus 1, right? So let's say I define my dp of I as the contribution of piece to cell I, right? So this is, let's say, cell I, this is cell I minus 1, this is cell I minus 2. So there will be a piece that will be contributing dp of I minus 2 here, right? Because we have defined dp of I is the contribution of piece to cell I. So there will be a piece of size dp I minus 2 here, and there will be a piece of size dp I minus 1 here, right? And there is probability of p into 100 that this dp of I minus 2 piece will move to cell I. So the contribution of this cell will be p into 100 into dp of I minus 2, right? Similarly, there is 100 minus p over 100 probability that my piece on I minus 1 will move to I. So it will contribute 100 minus p over 100 into dp of I minus 1, right? So you can sum both of these terms and you will get the contribution of piece at cell I. So you can say your dp of I is just p over 100 into dp of I minus 2 plus 100 minus p over 100 into dp of I minus 1, right? So using this, you can find the contribution of all the cells from 1 to n minus 1. Then your final answer is just equal to summation of dp of I going from I equal to 1 up to n minus 1, and then plus one extra move, right? So that will be the entire solution. And I think the very main step of solving this was to visualize that, like, you can see this as a game where a piece is moving through the cells from 0 up to n, and like when you have a probability p, you can visualize the piece just splitting up, right? The problem remains the same, you just have to sum the contribution of the piece, but when you have some probability p, the piece will just split up into pieces, and the answer is still just the sum of contribution over all the cells from 1 to n minus 1, right? And if you guys want to see the code for this, here is the code. So here is the code. I will take in two integers n and p. Then I will define was here. This is basically my dp, right? So was here is just my dp. Then I will define my was here of 0 equal to 1, right? Because initially the entire piece will be on cell 0, right? So you can see that dp of 0 is equal to 1, right? Because the entire piece will be on cell 0 initially. So dp of 0 will be equal to 1. Then I will go over all the cells from 1 to n minus 1. And my was here of phi, there is a 100 minus p over 100 chance that it will come from cell I minus 1. So I will do was here of I minus 1, contribution of p's on cell I minus 1 into 100 minus p over 100. Right, similarly for cell I minus 2, there's a p over 100 chance. So was here of I minus 2 into p over 100, that it will come from cell I minus 2. Then I want to add all the dp's from 1 to n minus 1. So I will add this to my answer and I will find its mod. Then in the end, my entire answer will be answer plus 1, right? Because this one extra move to reach cell n or n plus 1, right? So my entire answer will be answer plus 1, and I will print it out, and that will be my entire solution. So if you guys have some doubts, feel free to ask in the comments or join my Discord server. I'll be more than happy to answer your doubts there, and I will see you guys in the next one. Bye bye.